In the last video, we took a look at how the level data was stored in Eggerland Mystery. This time we'll take a different approach. Instead of figuring out how exactly a specific feature is implemented, we take a look at an interesting section of memory and try to figure out how it works and what it represents. The area in memory I'm talking about is located right here. As you can see, the game seems to be filling up this area, starting at address 0xD2D6, mostly with the value 0xof. It neatly counts from 0 to 15, or 0xof, and then progresses to the next byte, even though Lolo is simply standing there, not moving at all. In the previous video, the first thing we did was figure out where the current round number is stored. We used a cheat finder and figured out there were two addresses that consistently contained the current round number. We went with the first one because when we changed that one in memory, the game immediately updated as well. Now let's take a look at the second one. The address is 0xD2D4, which is suspiciously close to the area we are currently investigating. This is how the memory looks like when we boot up the machine and load the ROM. Of course, now in address D2D4, which contains the current round number, we have the value 56x or 86 decimal. This is of course the round number for the demo that will play if we wait a bit in the main menu. Let's now go to round 1 and see how this memory changes. So I will continue execution and I will enter a dummy password, so we will start round 1. Of course, the address containing our current round number now has the value 1 in it. We are, after all, in round 1. But something else has changed as well. Take a look at these two bytes. They contain the values D6 and D2. If we interpret these two values as a 16-bit pointer, we end up with 0xD2D6. We have to swap the values around because of endianness. Now, 0xD2D6 just happens to point at the start of the area we are investigating, where the marching byte occurs. Surely this can't be a coincidence. Now, let's start a round so we can see our marching byte in action. As you can see, the game is slowly starting to fill up this area of memory again with the value 0xof, except for the first byte. Something else is happening as well. If you look, as soon as we reach OF and the marching byte progresses to the next byte, our pointer updates as well. So let's pause the execution of the game and look at the value of the pointer again. The 16-bit pointer now points to D2DC. If we look at this address, we see that it is pointing to the location of the byte we're currently updating. That means that the 16-bit pointer merely keeps track of where we are in this array of bytes, in other words, our current position. Before we even look at the assembly, we are already aware of 3 memory locations. At D2D6, we have the area of memory in which the marching byte occurs. In D2D4, we have our current round number, which is most likely related to what we are doing. And in D2D2, we have a 16-bit pointer that points to where we currently are in our marching byte region. So the first thing we're going to do now is put a watch point of type write memory on the first byte of the area we are investigating at address D2D6. So let's do that. We'll go to watch points, click on add. The type is going to be write memory, of course, because that's what we're interested in. Then we'll add the address D2D6. And we do not seem to be triggering yet. So I'll enter my dummy password to go to round 1. And now we do trigger. Of course, the highlighted line is at 4273, but the thing that actually triggered the watch point is the line before at 4271. So if you look what's happening there, we are loading the hard-coded value of 1 into whatever HL is pointing to. So we'll look at the HL register in the CPU registers window, and HL does indeed contain D2D6, which is the first byte of the memory area we are investigating. Okay, so let's continue execution. And now the game seems to be ready to be started, and we're not triggering again. So that fact, combined with the fact that we're loading simply the hard-coded value of 1 into the first byte, leads me to believe that this just is a sort of initialization function and doesn't really matter when it comes to understanding how this area of memory works. So now I will start the game by pressing the down key, so Lolo starts moving down. Now let's see where we end up. We immediately trigger the watch point again. So let's look where we end up. In the disassembly window. Okay, so this was the thing that triggered the watch point. We're loading the accumulator, whatever value that contains, into whatever HL points to. And HL, of course, again points to D2, D6. So the first byte in the area we're investigating. Now this looks a bit more complex. We'll try to find the start of the function to see what we can figure out there. So if we look up, we have a conditional return. We have another conditional return. We have another one, and then we have an unconditional return. Now, most likely, this is not always the case, but most likely this will be the return belonging to the function above this function. So we can assume for now that this is the start of our function here at 447D. So the first thing we do in this function here is load C819, whatever is in there, into the accumulator, and we test it by ANDing it with itself and returning if that value is non-zero. So we're doing a Boolean check, so to say, of whatever is contained in C819. And then we do the exact same thing for D260. So we're ANDing it with itself, and we're checking if it's 0 and returning if it's non-zero. So this function starts with 2 checks, but we can assume that we're not failing those checks because we did trigger lower in this function. So let's continue on. The first thing we do now is load the value at D2, D2 into the HL register. And we've already established that D2, D2 contained the 16-bit pointer pointing to the current position in our array of bytes that we're investigating. And we need that, of course, we need the current position as a pointer into HL because that's what we're using to actually write out the byte. Okay, next thing we do is load the value of 0 into our DE register. That means that both the D and the E register gets put to 0. And if you look a bit down, we see that the E register gets manipulated as well as the D register gets manipulated. Those values or those registers are then ORed together, and the result is put into the A register, which we then write out into our current byte. So then we load the value at D2, D0 into the accumulator. That's an area of memory or a byte that we don't know about yet. We test it for 0, and we jump, if it is, to 4495, meaning 4495 is right here, so we are skipping this line if it is 0. Otherwise, so if it is non-zero, we load the hard-coded value of 80 hex into the E register. Then we load the value at D008, again a value we don't know about, into the accumulator. And then we double this 4 times. So we're adding it to itself. So we're doubling it 4 times. And we're loading that into the D register. It looks like we already have a good overview of what the first part of this function does. There are still 2 unknowns though, namely the memory locations D2, D0 and D008. We don't know what these contain yet, but they are significant because they fill up the D and the E register and ultimately get converted into the A register, which gets written into the byte array we are currently investigating. Before we try to figure out what these 2 unknown variables represent, let's convert the start of this function to pseudocode. We start with our 2 booleans at C819 and D260. If either of these booleans are true, or in other words, non-zero, we immediately return from this function. Then we have a pointer to our current position in our marching byte area, which is D2, D2. And then we initialize both D and E to 0. The boolean at D2, D0 gets checked, and if it is true, E gets set to OX80, and then the value at D008 is simply bit shifted to the left 4 positions. So whatever is in the bottom nibble gets put into the top nibble. For example, if we have OX05, that becomes OX50. There's no magic bullet when it comes to figuring out what exactly a completely unknown byte in memory does. Of course, you can put a read or write watch point on that location and start reading assembly, but sometimes that can get you multiple layers deep in code surrounded by other unknown memory locations and many calls to unknown functions. An alternative is to keep the memory window open to keep an eye on the byte and simply try different things in game. Once you see the value of the byte change, it then comes down to figuring out what exactly it was that you did to trigger the change in the value, either shooting a bullet or pushing a block or whatever. So let's play the game whilst also keeping an eye on memory location D008. We can immediately see that the value at D008 changes to 5. When I move up, it changes to 1. If I press the right button, it changes to 3. And if I move to the left, it changes to 7. Of course, if I stand still, it remains 0. So it looks like D008 is simply the movement direction that is being stored there. And there are 5 positions. Of course, you see it flickering between 0 and the actual value, but that can just simply be some debouncing that they implemented. That's not really relevant to what we are doing here. With the same way of experimenting, we can figure out that the byte at D2, D0 becomes 1 as soon as I press the spacebar, which I'm doing now. Of course, this value is also debounced, but again, that doesn't really matter. Let's take another look at our pseudocode. The variables d and e are now initialized a little bit differently. Variable e is now dependent on the spacebar being held or not, and variable d is now the movement direction that's being bit shifted left 4 times. Now that we know we're dealing with spacebar status and movement direction, we can move Lolo around in the level and take another look at our marching byte that we're currently investigating. So I will move down, and we can see the counter counting up. I will move up, I will move to the right, and down again, up, and to the left, and then I will pause. It looks like there are 2 conditions for the marching byte to jump to the next position. We already knew that once OXOF was reached, it would jump to the next one. However, now we see that every time we change direction, the marching byte also jumps to the next position. We know from looking at the assembly that the movement direction is stored in the top nibble as well as the spacebar status, because the movement direction was bit shifted left 4 times. The bottom nibble simply contains the counter, which we have seen before, counting from 0 to 15. Now we look at the data in our marching byte area. We start with 5F. 5 is of course down, which is the movement, and the F means 15 ticks. Then we progress to 1F, 1 being up for 15 ticks. Then 3, 6, the 3 means move to the right, and then 6 is the amount of ticks, etc. These actions seem to correspond exactly to what I was doing when I was playing the game. But the question remains though, why would the game need to store the exact timings of all the movements of Lolo in memory? We can figure out the answer to this question by putting a watch point of type read memory on the first byte of the area we are investigating at D2, D6. That way, as soon as the watch point triggers, we figure out what the game was doing, and we then also figure out what that area of memory was used for. So let's add the watch point. I will add a new watch point of type read memory at address OXD2D6. And then I will start playing the game, and we break immediately. The reason the game has to access this byte again now, and also why the watch point triggers, is because it needs to figure out whether the direction has changed or whether the time limit for this byte, as in 15, has been reached. As you can see, the next instruction we are going to execute is ANDing the current byte with OX70, which would extract bits 5, 6, and 7 from this value containing the movement direction. Once we skip processing the current byte, you'll see that the watch point doesn't get triggered anymore. So I will continue. I will hit play, and again we trigger, and again a 3rd time we trigger, but now you can see that the next byte is being processed, and we do not trigger the watch point anymore. It just starts counting up to OF, and that's it, because we're not moving. So I've waited around for a bit, as you can see from all the OFs in the data, and the watch point didn't trigger again. Now, if you know the game a bit, you realize that in the main menu, if you wait a bit, the demo plays, and it doesn't only play round 86, as is the default, but it actually replays the last level you play yourself. And of course, that's the answer to the question, why do we need to store all the movement and the timings? It's just so the game can replay your last played level. So let's take a look at the demo and see whether the watch point triggers there. So I will continue execution and then open the virtual keyboard and hit Control Stop. So we go back to the main menu and now we wait for the demo to play. And of course, it loads round 1, the last round we actually played, and it breaks immediately, accessing the value at D2, D6. I will now deactivate the watch point and let it do its thing. Okay, it did the exact movements that we did before. In order to prove that we're actually dealing with the demo data here, we can mess with, for example, the byte at D2, D6, the first instruction. That is currently 5-2, meaning we go down because of the 5, and it's for 2 ticks. So if we change that, for example, to 5F, that would mean that Lolo wouldn't stop where he stopped right now, but he would continue down for 15 ticks. So let's try that. So I will change the byte to 5F, and then I will continue execution, and we'll go back to the main menu, and we'll wait for the demo again to play. And now we can see Lolo running all the way down because of the 5F change we did. So that's it. We figured out exactly what the marching byte area represents. For each of these bytes, the top bit contains whether the spacebar has been pressed or not. Then we have 3 bits for the movement direction. That needs to store 0, 1, 3, 5, or 7, which perfectly fits in 3 bits. And then we have 4 bits for the timing. There's a little bit more information in my blog post about this subject that you can find at a link in the description. If you have any questions or remarks, you can put them in the comments below. And if you want to contact me, you can do so through my website or through Blue Sky. And if you want to support this type of content, then you can do so through Patreon. Happy reverse engineering!